Okay, good morning everyone. I think we may as well make a start.
Oh, are you joining us? I don't know what the questions are either, so...
Hey Chris.
Okay, right, well, my name is Alistair Basden at Durham University, and I'm part of DRI, which is the STFC-funded HPC facility that is going to have HPC sites in 4 different locations, one being Durham. And there we have the DRI memory intensive service, so about half a petabyte of RAM on our nodes, 70,000 cores, something like that. So that's where I stand. I think it's probably worth doing quick panel introductions as well, just because in case there are people who have just arrived this morning. So why don't you start? And
yeah, thanks very much, Alistair. So yeah, hi again everyone. I'm Bill Ayres, University of Manchester Library. I'm strategic lead for research data management. So my main role in the library is managing the research data management team, and then I also work very closely with colleagues in research IT and in IT and across the university. I'll be talking about, I'm sure, during the day. One of our main focuses at the moment is the Research Lifecycle Programme, which is our 5-year investment in removing barriers for research across all kinds of areas. So I'll be covering that later.
So I'm Peter Heywood. I'm a research software engineer at the University of Sheffield. I do mostly GPU stuff, and I'm involved with BEAD as part of the support group and the documentation task force.
Hello everyone, I'm Phil Hasnip. I'm at the University of York. I'm a lecturer and for the next 2 weeks a research software engineering fellow. Yes, I did start on April Fool's Day if you do your maths. Start as you mean to carry on, that's what I believe. I have a small research software team embedded in physics in the University of York.
Hi, I'm Emma Barnes. You've seen me a lot recently. I'm head of research and faculty IT at the University of York, so I lead a team of RSEs, embedded RSEs, and research infrastructure.
Cool, I'm Christopher Woods. I've just been thrown up here at the last minute, possibly because of something that might be very disruptive that's appearing with government and with every other thing that's happening at the moment. And in that sense, I am one of the new AI supercomputing infrastructure leads for the Isambard AI project. So, it was installed last week. It's very big. All of the things we had this morning in the first panel on how do you plan things, how do you get to your users, how do you... None of that. Because you just simply get money by you do AI. I haven't done my first computer thing, and I've missed that, but I would say my first computer that I programmed on was a Texas Instruments TI-99-4A, if anyone knows what one of those are. It's always fun because it has no non-volatile storage, so effectively it means when you program, you turn it off, and then it wipes it, and then you have to reprogram it the next time you turn it on. And then it was an Amiga. And very soon it will be a Grace Hopper, which is a slight step upwards.
yeah, okay, I didn't realise it was the first computer thing, but mine was an Amiga 500. Probably. Lots of you will remember them fondly. Right, so this session is about what lies ahead for DRI Tech. Now, this is the type of session that actually it would be easier for us to do this session in 5 years' time, and then we could tell you what did lie ahead in 5 years' time, and then there'd be a lot less hand-wavy and stuff. But anyway, we're going to try and tell you now about what lies ahead. So, first question for the panel here: what technology is likely to disrupt how we use and develop DRI components? And let's be focusing on 5 years, because beyond that it gets ridiculous, doesn't it? So what technology do we think is likely to disrupt how we use and develop DRI components? And let's ignore AI for now.
I go sit down then.
We'll because otherwise we'll ignore it, because otherwise that'll be the first every time. So we'll ignore it for the first maybe minute, and then we'll bring AI in. So someone think of an answer without AI to start with.
Can I then say that basically the biggest thing, which I think is going to change the way we program and we use our systems, is the movement to unified memory. So we very much used to programming our processors where we separate the GPU and the CPU, or the CPU and various accelerators, and they exist in separate memory spaces. And that kind of was appearing at the same time as you were seeing the beginnings of newer technologies beginning to appear in programming languages like C++, with the Mac M1, M2, M3 chips, where they basically have the unified CPU, GPU, neural engine in a single address space, and particularly with the Grace Hopper and the AMD processors coming, where the CPU and GPU is in a single unified address space, it creates a completely different way of actually thinking about programming the actual computer. And finally sort of NUMA-aware programming will be coming back into vogue. So with the Grace Hopper, particularly ones we'll soon be having, these are nodes where you have 4 Grace Hoppers in a single node. So that's 288 CPU cores, 4 hoppers, 512 gigabytes of CPU memory and 384 gigabytes of high bandwidth memory, where the CPU can read and write the GPU memory faster than it can read and write its own memory. This means you begin thinking of your application in terms of where you place the data in GPU memory, because you can just place it there and the CPU can still use it, so the first speed up is literally just put your application in GPU memory. Moving things between the two becomes a no-op, so your CUDA code that you were writing, which you were thinking of like the CUDA malloc, CUDA copy, that's now a no-op, it's just you just put it there straight away. But it also means you begin thinking of your GPU RAM almost like RAM, and your CPU RAM almost like disk, and then your network almost like campaign or something. And this whole way of like designing your applications, while this is kind of new in the the supercomputer land, we know that what's in the supercomputer world, what's in the consumer phones and the consumer MacBooks and things, those are going to become the bread and butter processors in the next 5 years. And I would think we would be seeing things like CUDA or sort of whatever other flavour of competition to CUDA that we have this year. Those things will just disappear as low-level languages, and you'll be really seeing people programming in kind of like NUMA-aware C++ with parallel C++, NUMA-aware Python, NUMA-aware other high-level languages, and there'll be, of course, a whole new range of languages which will be appearing that people are making use of these kind of interesting architectures, and that very much changes things. And of course, because it changes things, you'll also have all of the new interfaces on top of that.
Okay, thank you.
So I think I agree with all of that, except for maybe the timeline. I'm a bit more skeptical about CUDA disappearing in the next 5 years. It would be great if we could have performance portable code for GPUs, and especially with the upcoming higher bandwidth interconnect GPUs. But if vendors like Intel are still actually making GPUs in 5 years' time, we don't know if they'll have a GPU of that style yet, as they've already cancelled their announced ones. So I'm a little bit more skeptical, but I would like that to be the case.
Yeah, I echo that, but also just one day the things that are in supercomputers become on your phone and your commodity chip. I don't know whether that's going to happen in the next 5 years. Some of the roadmaps still have consumer kit having separate memory address spaces. So if you're in high-performance computing and you only care about high-performance computing and all your applications are on high-performance computing, I think absolutely this is going to make a big improvement, and it's going to make GPU programming much more like programming some of the more recent CPUs, and even not that recent, last 5 years, with where bits of the hardware could see their own RAM very quickly, and then it was costing you more to move a little further afield, but you could do it. But if we still have a world where your laptop and your workstation has memory on the GPU and memory on the CPU and PCI Express between them, then we're still going to have to care. If you're an RSC supporting lots of users on lots of different hardware, unfortunately, having some platforms with unified memory and some platforms without might make life extra complicated rather than extra easy. Obviously, after 5 years, it'll all be fine.
And then can I also add a second thing that I think is also a big sort of conceptual change, is that the number of transistors that's appearing on a chip is now pretty much more than the power you can actually push through that chip. So we already see this in the mobile space, where effectively you don't power the entire mobile processor, and different parts turn on and off, and you have to be careful in the programming of a mobile chip to be able to basically get most performance and really think about your power budget as you're working. We're going to see this more and more with the interesting chips which will be coming out from various vendors, and you'll be having to really think about how using different features of those GPUs and CPUs will actually clock down or clock up different parts of that individual processor, because there just physically isn't enough power, enough heat dissipation to actually keep that entire thing going all in one go. And I think this, again, is just going to keep ramping over the next sort of 5 years. And we used to be thinking that we were constrained by memory or constrained by CPU or constrained by bandwidth. I think power is going to become the thing we really need to think about, constraints and how you do cooling and all of that jazz.
Okay, so what about on the anyone got any ideas on maybe on the storage or the network side of things? We talked about compute. Anything on the storage and network side?
Storage is lovely. Storage, we're actually going through a renaissance in storage. I've become I was very down about storage for a long time because nothing was really happening. But now that we have NVMe over Ethernet, it means that you're having really interesting storage products like VAST appearing, where essentially you're able to disentangle, effectively have one super node made up of several individual separate nodes that are all NVMe over Ethernet connected to lots of SSDs. And what this means is actually it's a single kernel seeing a single set of SSDs. So they don't have a network communication between them in the same way because it's basically like an extended PCI connection. And so you end up creating storage products that almost treat network storage as being local storage. And so you get these huge speed ups and efficiencies and various other things. It also means that object store becomes much more realistic as a large scale proposition. So one of the things that you'll be seeing with Isambard AI is that we will be having 20 petabytes of all flash Lustre store, but that's complemented by 7 petabytes of all flash VAST object store. The benefits of this movement towards object store and this kind of revolution is enabling us really to properly do multi-tenancy of storage. And I think multi-tenancy is another one of these things that's really going to be hitting us over the next 5 years, meaning to think how you multi-tenant your systems. You want multi-tenancy for a number of reasons. One is the ability to segment different users and enable to give effectively root to a user so they can be in a space which you as an admin can't see, which is what you need for SDs, TREs, and kind of like sensitive industrial workloads. But also this multi-tenancy approach also enables you to build proper zero trust infrastructure. As we begin to think about more how security needs to come into the DRIs that we're building, you need to be designing them with the view that your users have a compiler, and because they have a compiler, there's no point whitelisting your software because they can compile anything they want. That means if there is a kernel privilege escalation bug, a 0-day, they will get root. And you have to begin designing your systems with that view, and multi-tenancy enables you to begin these kind of blast layers of protection. So I think, again, that's a thing which will really disrupt the way we work and the way we think and design systems.
Chris, any other thoughts on the storage front? No, right. Any thoughts on the network front?
So I come in here. I mean, network. I think those of us who care about networks from a performance point of view have seen lots of increases in bandwidth and no change to latency, and that's very bad. Some of that's fundamental physics, which as a physicist I feel responsible for, but we haven't yet managed to change the speed of light. Working on it. But there are things that we can slow it down. We can change the speed of light in the way we don't want. So if we could just, we could also work on changing the hour of time, which would also work. It's one day. But what we have seen more recently is cleverer things on the network. So things that do some computation around the network, things that do smarter routing, things that can predict routing, things that can do reduction operations where you're summing over lots of component programs. They can do that, and you can offload that to data processing units. And some of that's really, really interesting and can mean you save CPU time, but you can also send network bandwidth because you can do some on-the-fly compression. You can do some compute, not a huge amount yet, but that has the potential to change a lot of what we do on really big systems. And there are also things now coming along that might be interesting around ways to connect in sort of software particular resources, so you could have a set of GPUs somewhere not physically attached to your machine that you could configure dynamically to be as if they were attached to a machine, and that could change some of the ways that we do kind of medium scale computing as well. We're a long way from it affecting your laptop, I think, but it offers a lot more possibilities. The idea you could just say, actually, how much RAM does your node have? Well, how much do you want? I'd like to attach more RAM to this node today and a GPU, but not tomorrow. Tomorrow I don't need that much RAM and I don't need those GPUs. And the idea that we might have a system that could be configurable at that level is quite exciting.
Yeah. and that's something that's here but not yet. You don't see it on scale yet. It's there. It's in production but not on scale. Chris.
Then on the network thing, and again, you can tell I've been very heavily buried in technical things for the last 6 months. One of the really cool new things in networking at the sort of supercomputing scale is the fact that now multi-tenancy and network segmentation is properly in things like Slingshot, and I think we'll see this move into generally clusters as well. So the Slingshot Slingshot 11, which is one we have, that basically enables you to properly create VLANs and create VLANs on demand. But the other thing which is really nice now in the Slingshot architecture is these things called VNIs. And what VNIs do is basically provide a token and an address, a network space for an application. So effectively all traffic between applications is secured by the token, encrypted, and also the switches and the endpoints note only route traffic to the processes which actually have those tokens. So you're able to build properly segmented per process based things running at network, slingshot latency with 100 gigabytes per second between the nodes, which is just incredible in terms of you think of the speed. But this kind of movement to us having now supercomputing systems that can behave like clouds and that have this high level zero trust multi-tenanted security in, percolating obviously from the top down with these very high-end systems. This is all going to percolate through, I think, through the entire stack, and we'll be all, I think, beginning to build these kind of systems over the next 5 years.
Could I just add, I realised we're talking high-performance computing, and not everybody here does high-performance computing. So Slingshot is the network that Cray offer, so it's the way of linking the nodes in a Cray, and Cray are kind of leading on some of this, but there are other...
Yeah.
This is something that's going to be rolled out across most high-performance networks. But if you're not in that world, if you're at a smaller scale, this isn't going to affect you, at least for a while.
Although I'd say that the concept of building clusters where you can segment networks and create sort of isolated VLANs and have all of the network traffic being encrypted, and the concepts of encryption at rest and encryption in motion, I think those will be feeding into network design and sort of cluster design at pretty much all levels, I think, as we go through the next few years.
Yeah, so if you're doing work that's commercially sensitive, for example, or medical work, or anything where you need some data security, that could make a big difference to the kind of way that you have to operate.
I would say for all, because it's actually about building zero trust systems. So if you build a completely open layer 2 network and you have a privilege escalation in one part of that, by not having these systems, you've basically compromised the entire cluster, and you've exposed all the workload regardless of whether you've decided it's secure or not. But having this idea of being able to build segmentable systems where by default the blast radius from the compromise of an individual user's job does not impact any other job on the system or expose data. It's those kind of ideas and thoughts as you're doing system design which I think are important.
Good. Any other thoughts from the panel? If not, let's think now about, we've avoided AI, but let's think about AI. How is that going to disrupt how we use and...
Can I just throw one thing in before we get to AI? We will get to AI. Just one thing I realised we've kind of glossed over, but actually there's a big shift from x86 to not x86. So, we're all, for a long time, we've been used to a computer is an Intel or an AMD thing. And a lot of us grew up, when we did our first computers, not many people, said a PC, which is probably as much to do with our age as anything. But and we're seeing some things again. I mean, Amiga 500 with a dedicated video chip and sound chip and offloading some things to those. I mean, those days are over, surely. So these things do come in cycles. But ARM is having a resurgence with NVIDIA, for example, with Grace that Chris has mentioned. And I think and Apple with the M1 and the M2 and the M3. So we are seeing a shift even at the phone level. We've had this shift, and at the laptop level we're having this shift now on the workstation level. And some things we do that will affect. It's maybe not completely disruptive because it's not new historically, but we have had probably 2 decades of not having to worry about what CPU you were using. Anyway, we can get to AI now. Sorry.
Well, just to comment on that. I mean, RISC-V is another one, isn't it? And there you'll see systems that look to the compiler order look very different, because depending on what RISC-V chip you've got, it's got certain components in or not got them. might not have floating point, might, stuff like that. So that's another. Any thoughts on that? Or are we desperate to get to AI?
I mean, I would say I thank Apple so much. I mean, obviously Bristol were kind of like the first kind of tier 2 site where we were going with Isambard 1 and really trying to bring ARM into the sort of the HPC space. And with the Mont Blanc project going back before that, kind of like how to actually make an ARM processor suitable for fat workloads rather than just mobile workloads. That's really paying off now, but it paid off because I think Apple basically committed to ARM, and it meant that because a lot of researchers, a huge percentage, use ARM as their laptop, the entire Python stack went across, the entire R stack went across. You had that chicken and egg problem solved effectively through Apple, to the point that actually I'd forgotten about it. I mean, I'm on ARM pretty much all the time because I'm just always on Apple. I think it's interesting because monopolies do come and go and things will always change. And I think it's a reminder to us all when we're kind of designing our systems, particularly software, which is lasting decades, that it's always dangerous to tie ourselves to what we have today. We always need to be looking 5 or 10 years in the future. And so when I say things like, CUDA will evolve and NUMA will evolve, I'm always thinking actually what will I need to be coding in today for my code to run in 10 years time, 15 years time. And that is a very interesting world where you don't have static processors. A chip is a system on a chip. It will be made up of multiple units. Neural engines today, but who knows what other things will be tomorrow. And it's an interesting. It's like a fun time. I'm really pleased that we've gone past like 2005 to 2015. I found a very static period in DRI. Who might disagree with me, but it felt like it was nothing was much changing. And now we're going to this world where network, storage, processor, accelerator, everything is completely changing. And while that can be scary, I just think it's very exciting. There's a lot of opportunity for us to really guide people through some quite big changes.
Good. Right, okay, so I think we've bypassed our time for AI, so we can skip that one. No. If anyone's got any thoughts about how AI is going to disrupt what we do over the next 5 years, let's get some thoughts out there.
I know people are looking. I want to give other people a chance to.
Let's let Chris give other people a chance. Yes.
Can I jump in from the library side? So I'm but a humble librarian, but one of the things we found, and we've been doing this in the broader team that I'm part of, the Office for Open Research at Manchester, is that, and it's is this cheating? I'm aware that I'm in a room full of RSEs and people that do this professionally. Some of the AI tools that now exist are really helping team members who don't have those kind of skills to be able to do things. And I'm not talking about replacing roles or taking stuff away, but to do things like building simple connectors between APIs without the skills that you would normally need as a developer to do that. We've been looking at things like we're calling it a sprint, where we are using things like Jupyter notebooks and AI tools to help run projects and to just lean into that as a thing that removes the kind of some of the legwork and the hard work and the kind of well, I'd say the boring, but the stuff that is not an interesting part of a project, and using those tools to help us to do that in a way that we've not been able to do until they came onto the market. And particularly, obviously, everyone says OpenAI, but Chat and GPT. That's the thing that's really opened this up for us. And the final point, maybe from me, particularly, is that what we found is that for newer members of the team, and in our case, some really young members of the team who've joined in relatively kind of developmental roles, they've been able to lean into this and really find they can bring value to what we're doing quickly, which is fascinating. So that's something that is, in the library side of things, is really changing stuff quickly.
Yeah, I think from our side, it's so kind of messy and changing at the moment. It's very hard to keep on top of it, and we do get people asking for recommendations from us. What should we use? Why should we use this? How does it work? Should we use this for our research? That sort of thing. And we're trying to keep up as much as everyone else, and also do our day jobs and do other things. And it's also very difficult for us to necessarily, at the moment, give a recommendation. And there's still a lot of catching up to do from the ethical side as well, and the security side. We don't really have any so we have some policies, i.e. don't use it in exams at the university, but that's where it kind of starts and ends. You know, we have to really consider the impact and effects of using a particular tool, and please don't put your personal data in that, and please don't put anonymised, you know, things like that. So there's a huge amount to learn, not just from a technical point of view, and where you can actually use and embrace it. And I think we should embrace it. I think we're going to have to embrace it. I don't think there's no way about it. But also making sure that people are using it in the correct way and in a safe way, in a way that is actually giving you the answer that you should be getting, not a lie. You know, it's not perfect, and you're still going to need domain knowledge in your area to check through. Yes, you can convert some Fortran to Python, or, you know, using some of these tools, but it probably won't run, and it might give you the wrong answer. So you still need to know how to program. You still need to understand your code. So I think that bit worries me, because I think people are kind of seeing it as this oracle, and it's giving the correct answer, and it's the output is correct, and it's not. It's really not, and you still have to check. So there's a lot of work that we have to do around that particular area.
I have kind of two perspectives.
No, go for it.
I have kind of two perspectives on that. First, I don't like using the word AI, but I'm now contractually obliged to use the word AI.
But use it responsibly.
I'm now machine learning. I prefer machine learning.
Yeah.
Also, anyone who wants to, it's really easy to learn in terms of how it works. So I really recommend the YouTube video series by Josh Starmer called StatQuest, and he basically explains AI using cartoon characters. It's massively entertaining. He's a bit mad, but you do actually see it is just stochastic gradient descent fitting small bits of a curve against a massive hypersurface. It really is super, super simple. First perspective is that scale made it work. So the reality now is, 5-10 years ago, I would have gone and I would have spent my time really crafting a wonderful algorithm because I can beat the machine. Now, if you have enough data and there's a pattern in your data, machine learning will find that pattern. There is no point you trying to beat the machine. The machine learning will find the pattern. Any data set you want, if there's a pattern in this data, the machine learning will find the pattern. It doesn't get it right all the time, but it will find the pattern, and you can extrapolate that pattern. And the tools to find the pattern are ridiculously easy to use, which is why you can just basically give it to somebody in a Jupyter notebook, and that's really transformative. The second perspective I had is I was right at the beginning of the Excalibur project in the SAT with Susan, basically coming up with why Excalibur was funded. And Excalibur was funded to basically do the mathematical development work to port our codes to what we thought to be the future exascale systems. And there was kind of one viewpoint that this was like finding new algorithms that would enable CFD to break some of the barriers of those exascale systems. And what I find kind of slightly ironic is actually what happened is the exascale codes are the AI codes. And what's happened is those AI codes are being used to find the patterns in our simulations. So it's really common to do a CFD and use AI to learn the model so it can then upscale, and using AI as an accelerator. Or a project I'm very heavily involved with pharma, which was basically using AI to learn the whole of quantum chemistry, run every single quantum chemistry calculation you can, learn all the patterns in that, and then you just put in the coordinates of the atoms and it gives you the forces and the energies pretty much correctly. And it means you can then do quantum chemical simulations dynamics using the MLNet. All of protein folding was placed into an MLNet to do AlphaFold, and it just worked. And that is the shift. That's how we get to exascale. It's by actually going, no, we're not just going to make our meshes one level more refined, a little bit finer. We're not going to run our simulations a bit longer or go below one level of theory. It's where we embrace the fact that the machine can find the pattern, and then we train the machine using our physical models, and you have these converged machine learning physical simulations, which is why we went down the Grace Hopper architecture, to make sure you could run the simulation and the AI at the same time, because that's where I think most of the value is going to be. Every single research domain is going to be using machine learning. We're at the start of, I view it very much like in the end of the 1970s and 1980s, where somebody stood up and said every single business will have a computer, and they pointed at the computer and went, no, we don't need that computer in our business. Every single business is going to be using AI. It's not a bandwagon, it's not something that's going to disappear in 3 or 4 years' time. what will happen is we'll stop talking about it because it will just be the thing that everybody uses. And it means that you'll be working with systems where you're actively thinking about how you're training the system. You'll be actively thinking about what the inference is and how much you can trust it, but also you'll be working with users who for the first time can actually take a computer and make it do what they want because they can tell the computer in English. And the computer can then do stuff that's magic, and part of it is then training them. How much can you trust that computer with the answer they've got? It's completely transformational in the way we work. And that's why some people call it as a democratization of DRI, why the health sciences, the arts and humanities is absolutely amazing for them.
Hey, Chris, any other thoughts on?
So I do think there are certainly some ethical and potentially legal issues with the current use of sort of trendy AI that will need to be taken care of, so software licensing breaches and things like that. Obviously that's going to end up in the courts at some point, so it's probably not going to be up to us, but we might need to be careful in how quickly we adopt some of these things. And on top of that, in terms of ethics, the enormous, although we can find these new algorithms and brute force, for lack of a better word, our way to the answers, that uses a tremendous amount of power to train some of these networks. So with everything else going on, that's maybe not the best idea. And on a slightly different angle, I think it's probably a good thing in terms of performance portability of GPU codes. So traditionally everything is written in CUDA for NVIDIA cards because they committed to the software ecosystem 10, 15 years ago, and other vendors have been playing catch up ever since. But due to the demand for GPUs for machine learning, if your lead time to purchase an NVIDIA chip is north of a year, you might end up seeing more AMD or Intel cards kicking around, and force the software to be portable, which is a good thing in some ways.
I think if I could comment on a couple of those, because I think I'm not going to say much about what the rest of the UK government does and how well they do things, but one thing the UK government did which was very good was they created the AI Safety Task Force, and they really viewed AI through that lens. So the AI research resources are not funded via UKRI directly. What's happening is actually it's through the UK AI Safety Task Force, through DCIT, and the AI Safety Task Force is our customer. And so everything has been driven through the lens of how do we do AI safety, how do we do AI ethics, how can we develop these things in a responsible manner. The other side was also this strong push to make sure that we're not burning carbon for no reason. So the systems which are being put in place, they're not designed to be run utilization all the time. It's not like you burn 5 megawatts because you want to burn 5 megawatts, they're burned for a specific output. And the actual entire design of these systems was about making sure you had these liquid-cooled containerized data centers with a PUE, I think it's about 1.03, 1.04, where you almost have free cooling, below particular temperatures, and where we have plans of how you then take the heat and use it in district heating circuits to actually heat, the surrounding area. So really taking that whole sort of sustainable design, because it is a huge amount of electricity, and we really need to think about that, which I think comes back to that first thing of like, what's the big change we need to think about? We need to be presenting this environmental cost of our DRI to our users. When you rock up to Isambard AI, you will not be like, I'm going to run a big job and it runs a month and blah, blah, blah. You will actually go through a process where you will actually have to demonstrate that you thought about this and there's a value before you'd be allowed to spend a month using 1,000 GPUs, because the environmental cost is too big. While we're nothing compared to Elon Musk's how many billion GPUs and all the other systems which are massive, I think it's imperative that because we are the academic community and we're very visible, that we're seen to be taking a lead on sustainability, because then, if we're not doing it and we're the ones saying climate change is real, which of course it is, then why would anyone else do it?
Yeah, I just want to make a point. Sorry,
Yeah,
were you speaking? I couldn't see. No, you go first, Bill.
No. I'm going to move on, so if you...
Oh, no, I just want to agree with that. And I think we also need to become more clever in terms of how we build our data centres, where we're putting our compute, what can we use, can we heat up swimming pools? People are already starting to do that. District heating, I put ours in Sweden, so where we use the heat to dry sawdust. This is a problem which is only going to get bigger, and as you say, as working in universities, we'll be for the public good, we have to, and climate change is real, so we have to be shown to be trying and making a difference and trying to change how we're working.
Can I just add one thing to this?
Yeah, go for it.
So I absolutely echo all the comments have been made. Maybe the hook that we can hang this on to, I know one of the things at Manchester, we have one of the university's kind of key visions is around social responsibility. The whole environmental sustainability aspect is married into that. I think it's exactly what you said, Chris. This is where if we show the way and show how this can be done, and I'm thinking, and we've talked about it across the whole of the infrastructure that we think about. So I'm saying not just the data centres and computational stuff, but if we think about the work that takes place in facilities, in universities, in terms of data generation and experimentation and so on, if we can look at ways that they can join up and really fit into that in a way that does demonstrate a commitment to sustainability in terms of the environment, then that will be a real breakthrough, because we're nowhere near that at the moment.
And I was so pleased that sustainability was one of the key things we actually placed into the tender. And we even went through the actual hardware. We have the full recycling, so Isambard AI is not going to be dumped in some random country. When it eventually reaches its end of life, there's a proper recycling facility up in Edinburgh where the kit is going to be sent to. The pods have been bought with a longer lifespan, so they can have next phases going at the same time. So it's one of the things I quite like. If you go 10 years back, sustainability was an add-on, and kind of you really had to fight for it. But now it's just embedded in all layers of sensible management.
Okay, so now, very quickly, let's think about quantum computing. So the question that I have for the panel is, do you think we're likely to see any disruption from quantum computing in the next, say, 5-6 years? And then even quicker, if the answer is yes, then what do you think that's going to be?
No.
I mean, the running joke is it's a decade away and will be in a decade. But I mean, I do think some quantum computing is likely to be a component of what we're interested in for some problems. I don't know, I'm hedging a lot there. But it had all the hype that we're seeing AI have now, but hasn't delivered like AI is already delivering, if you see what I mean. So I think that might be a good thing for quantum computing. The limelight has shifted onto AI. That might let people actually get on with solving problems in quantum computing without feeling the need, this pressure, to live up to this hype. We saw the thing with D-Wave and how that was going to change the world, but it was a quantum computer, or was it? We didn't know. Oh, sort of, but not really. But quietly, unless you're in that area of physics, but quietly, there are advances. People have done some quite amazing things. So I think something will come along. I'm not sure whether it'll be in 10 years for most of us, but there probably will be something we could get our hands on in that timescale and play with it.
Excellent. Any other comments on that? If not, okay. So next, let's moving on to a slightly. Oh, yes.
I don't work for any quantum computing company or anything, but I'd like to mention that the first QPUs, photonic QPUs, have been delivered in data centers in some places. So that might be a factor for scaling even before those 3 years. If someone can fill up a data center with quantum slices, we might see things that are unexpected so far. Thank you.
Yeah, I mean, my no is essentially there's no such thing as a free lunch, and noise and decoherence. I'm a quantum chemist by background, not a quantum physicist, so I defer to my physicist people who will tell me I'm completely wrong, because we have a very
It's a
weird
barrier,
quantum
yes,
chemistry.
of course, but it can be penetrated quantumly.
Yeah, but decoherence is very, very hard to maintain entanglement. And when you look at the quantum computing field, they originally started with real qubits, and then you just cannot physically prevent noise from getting into the system, so then they ended up with virtual qubits, and then you still can't prevent noise from getting into the system, and so it just keeps expanding and expanding, the pain you have to go through. And when you look at the algorithm, the real benefit quantum computing has had actually on the field is the quantum-like algorithms that were developed and actually showing how you can run a classical computer with a quantum algorithm, which doesn't need to be the exact right answer. And there's been massive advancements in algorithms where you've said, actually, we don't need the full answer, we just need the probabilistic answer, and you can then simplify the computational complexity of various things. And then it's kind of like, well, what's the quantum computer then going to be used for?
The same goes for AI. It's just multiplying floating point, half precision, 1 bit precision fast. There's nothing else to it by that look.
Exactly,
Thank
and that's
you.
why I call it machine learning. And when you look at it, it's literally just curve fitting. Somebody's just taking, if you look at it in one dimension, it's just fitting a 1D curve, and then you extrapolate from that. That is all AI is doing now. It's not conscious, it's not magic, it's just finding a pattern and extrapolating. And as long as your data, kind of like you're extrapolating into the middle of your data, it's fantastically good. As soon as you go off the end of the curve, it's fantastically bad.
Okay, good. Thank you. Let's move on now, because I'm very conscious about time. Do you think in the next 5 years or so there will be any new DRI roles as a result of some of these changes? And how do you think our roles will look different in 5 years' time?
Anyone want to be a prompt engineer?
Prompt engineer, yeah, very good.
I mean, I do think there is going to be, at least for the kind of 5 years, 10 years, there will be people, we are going to need people who understand AI and know how to make AI do things. The AI is developing more and more so that you don't need those roles. I mean, that's kind of what we were saying about democratization. But it is an amazing way to encode kind of what we would call intuition and experience and bring that to people. But I think there will be a role for specialists who understand when it's likely to be reliable and when it isn't, beyond asking the AI itself, are you reliable? Because confidence is not something they lack. But I think that we will need those roles, and we can't, well, whether we use AI ourselves, we will be justifying not using it if we're not. We will have to defend ourselves, and we will need
sort of like a
specialists.
research ML engineer or something. Could be a new community there. Couldn't it?
Yeah, I mean, to be honest, I mean, I don't want to give away the panel I'm involved with, which is the building a career pathway and everything else. But actually, part of Isn't Bad AI was creating a completely new job family. So the job, these are basically called AI supercomputing infrastructure engineers, specialists, and leads, and there'll be a support engineer at the bottom. The key thing is that this actually blended DevSys, DevSys, Net, and MLOps engineers into one thing. An MLOps engineer is actually one of the key roles in this, to actually build and prune AI ML systems and understand how to do MLOps. And MLOps is something which tends not to be done in academia. It's basically how you do ML in industry, which is where you do proper experiment tracking and rerunning and productionizing of the ML once you've done through training to then go to inference and then checking of this. Those are massive professions in industry which we're now bringing into academia. But I think there's a blending, as we've seen with software-defined infrastructure, removing kind of the pure sysops to basically become more DevOps, and the RSC kind of bringing some of the domain expertise into coding, and now the MLOps coming in. I think what you'll have is careers where people don't have to say, I am now just a systems engineer. You'll be like, you're now working in these multidisciplinary teams and then moving through your career across that very wide stack now, and hopefully with less siloing between the research infrastructure engineers and the research software engineers and blah, blah, blah. At least that's what we're trying to do within the Isn't Bad team.
Excellent. So leaving AI aside, do we think there are going to be any new roles other than AI, and how will our roles be different? So we talked about storage, compute, network, various other things.
Compliance officer. And again, the compliance officers will need to be embedded in teams, because the legal framework around compute, particularly, don't want to use the word AI again, but the hardware that we are using now is subject to export control laws. It's subject to a lot of legal frameworks which are appearing because of AI. People are now taking notice of the computational power we have and who we're giving it to and what domain it's being used in.
And even some of our software is subject to export control laws.
Exactly, and so it means basically it's impossible for us as DRI professionals to actually have that awareness. We're not legal people, and so actually bringing compliance into the DRI team, bringing cybersecurity into the DRI team, those are things I think which are just going to evolve and grow.
Can I just add, maybe in that topic, that this sits, to me, that the aspects of compliance and being able to have the view of regulatory aspects and things like export controls and so on, it can sit within the role of a data steward. So one of the things we're investigating at Manchester is bringing in data stewards into projects at the point of need, and they are necessary at the moment in kind of FS, in engineering and in areas where that kind of stuff's happening. But this is part of the, data stewards can perform a multitude of different roles depending on what's needed, and certainly I think, as we talked about in the first session, the response to the cyber incident and the changes that are going to have to be made to the way researchers work, in our setting, but this is the same for everyone, in terms of security and compliance and making that work for researchers without being a burden. Those kind of roles to help them do that when it's not them having to do it, it's not being placed on researchers themselves to have to do this work, are going to be really key to making all these things happen in the future too, and certainly within 5 years.
Yeah, 100%. I mean, this is actually one of the big changes that the research community is going to have, is suddenly having to be aware of the law. And most academics, they think that they're being told you can't do something because IT is being nasty or because the university is being nasty. No, it's the law, and we're trying to stop us being prosecuted and you being prosecuted. And the law is horrible. I really don't like having to go through it. And it's almost like when you can actually sit down with the academic and say, this is the law, and you take them through, they finally understand, but you can't do that at scale. And so it's how can we build positions within DRI and roles where you're actually, when you say give it to the data steward, you're passing a lot of legal responsibility on the data steward. So how do you educate them and actually what they're taking on? And if you did, would they go, actually, I don't want to be a data steward anymore?
I mean, there's also, if I just say, there's maybe not a new role as in a post, but I think a lot of us have started to become more involved in open science and interoperability and things that probably more than our colleagues who are purely on academic research. So I think some of these areas, we're probably going to take on some of this. We're going to be more aware of legal responsibilities and things, because we're also more aware of how to write our outputs in a way that a program could read them, and we could archive them and have a structured database of the knowledge and things. So the kind of things I imagine a lot of people in the room have been worrying about, fair data principles and things. I mean, in a way, some of this is an extension of that, and working not just openly, but if you like, safely and legally and openly as well. In some sense, it's part of that broader. We spend a fortune generating data. How do we make sure it's used ethically, but also on the other hand can be used by other people?
Okay, very quickly, any other thoughts on new roles?
We've got
If not, yeah.
The internet is taking over.
Yeah, okay.
You could all be attacked at coffee, so the internet is taking over. So we've got a short question from Will. It says, what is VNI that Chris mentioned?
So
it says, what is VNI?
Oh, VNI, so, and I should have, as you said, it's Slingshot. VNI is virtual network infrastructure, I believe it is. It's a component of the RDMA networking protocol. It's used by Slingshot, which enables packets to be routed securely to applications in a way that only the applications can decrypt it, but also only those packets are routed to, so that the packet doesn't go anywhere else on the network. So it'll be a way of creating very secure supercomputing networks.
Right, so next, James has asked, he wants to know your thoughts on AI and security, and both the good stuff with anomaly detection and the bad stuff with producing incorrect answers.
So for anomaly detection, Isambard AI's monitoring suite actually has an AI monitor, so it is built into just by HPE. So every time anything weird happens, it actually will be alerting on that. One of the weirdest things that will happen is we'll be rolling in Isambard 3 halfway through Isambard AI running, and hopefully it will say, oh, the temperature's changed. And that's cool. I mean, this is the thing, you can't film, there's so much data, there's terabytes of data of monitoring coming off these machines now. Or not cool. Terabytes of data coming off these machines. Humans can't look at this, and I think AI is going to enable you to basically do a lot of data scanning that you just couldn't do as a human. In terms of security, unfortunately, it also means that all of the threat actors have this as well, and so the threat landscape we're all going to face as DRI professionals is horrible. Like, now you can realistically do phishing attacks, you can create prompts, somebody could go onto ChatGPT and write a script, like ask for a prompt to basically find all the vulnerabilities in your service, and it will be found. And we used to do a lot of things because by security through obscurity, we used to do things by, our system's so small it's not worth anyone targeting it, in the same way like there's no point worrying about CCTV because there's too many CCTVs, nobody's going to look at it. Now AI looks at all the CCTVs, now AI will look at every single endpoint that's exposed on the internet, and it will just go through and find your holes. And I think that's going to be, again, a massive challenge. Yeah.
I'm going to have to apologise to Fernando because I still have more questions and he's in the room and they're not. So yeah, I basically just heard horror stories about skills startups and all the code in AI and people storing passwords. So it's sort of like the use of machine learning in security is fairly, not surprisingly, opaque. And do you have opinions on how you can make it more visible rather than being opaque?
Yes, so we have a cybersecurity masters at Bristol. I think actually building AI cybersecurity into training programs will help. Cybersecurity has to become visible, so I have to leave on Thursday night, tomorrow night, because I basically am in a cybersecurity workshop all Friday, pretty much. It's something which we just have to talk about, and I think we have to make visible. And it is going to completely transform the way we think of our systems, because you can now do things that, I mean, what was the Devon, the software AI, the software engineer AI, where basically the prompt was just go and fix this GitHub issue, and the AI itself was able to go out and basically scan loads of GitHub repos and download lots of things and make lots of potentials, and then iteratively do the thing it needed to do. You have the skill of an attack team at the back of a prompt. That's not, Alan talking about being kept awake at night. That's the thing that keeps me awake at night. If we get hacked in the first 3 months, we're dead.
Yes. I still have 2 more questions.
Can I just make a comment on that one as
yes,
well?
Please.
I know you talked about master's levels cyber courses, but I actually think it needs to be from primary school even. It's almost like the advent of social media became a massive thing, and then we've had to educate our children, users, people on the good and bad points of social media. I feel like this is going to be a similar process, and the sooner we start educating people, and that should be children. I've got a son, I want him to use the internet, I want him to be involved in this stuff, but I want him to do it in a safe way. Because there's a lot of good parts, but there's a lot of bad parts as well. So I think we have to start that education, because when he's grown up, this will just be a normal thing. It'll be everywhere. We need to be educating people on cyber, on the impacts of certain technologies and things like that from a very early age, I believe.
And what makes it worse, just to add in, the world 10 years ago was lovely. The world now is not so lovely. Mm-hmm. We openly have people saying we are a pre-war generation. Yeah. Cyber attack is something which doesn't trigger Article 5, and so it is ongoing. Mm-hmm. And I'm not going to name countries, because last time I did I got into trouble. But we are living in a world where we're actively at cyber war. And that's a very different world to we were 10 years ago, and the threat landscape is very different. And during COVID, the DRIs were hacked by countries I won't name to slow down the development of our vaccines. We are critical national infrastructure. Universities are being classified as critical national infrastructure. That completely changes the security and threat landscape and the way we have to respond. And as I said, the way the world is changing and what's going to likely happen over the next 2 to 5 years, very sadly, is going to cause us to have to work in a very different way than the way we're working in the 2010s. And I do think it's really sad. I like the global citizen and we're all friends and everything else, but the world is not that world anymore.
Fair enough. Now I'm the messenger, please don't shoot me. Tobias says, and I'm going to say this out loud, read this rather than any cutting it up. I think there's a lot of wrong statements here. Shared memory is not the future. It is the future for a compute centre without financial constraints who can invest in the underlying network technology. Can the panellists please provide cost estimates tied to their statements? On you go.
So I would just point to the Apple M processors. I point to the iPhone processors. I point to the way that the ARM processors, you're shared across multiple, basically memory being embedded on the chip, and the different units on that chip addressing it are the thing. That's the consumer space. The idea that DRAM is going to be bolted onto the motherboard, I think DRAM as a separate thing is just going to disappear, because that's not where the consumer space is, and the supercomputing space always follows the consumer space, ultimately, because that's where the money is.
Can I just jump in? I mean, I don't think we were seriously saying that shared memory across many, many computers was going to be the way forward. So I think in terms of the network, that bit of the question, I mean, there are a few niche machines. I don't think that's going to be the future. I think we're talking about shared memory on, let's say, a workstation, a PC style thing, where the same memory can be seen by whatever CPUs you have, but also whatever GPUs, whatever quantum processing units, whatever, you know, everything starts moving more in that direction. And that's going to have a relatively low cost at the workstation level, because if you buy an Apple, you don't get any choice. That's what it does. And it's where most of the vendors are heading, not all. And it's not obvious that will be the only one. But I think the cost is probably not a primary driver
It's
factor.
the difference between unified and shared memory, isn't it?
Yeah.
Yeah, so unified. And again, a
Unified.
Grace Hopper now is £50,000 retail, I believe, or £75,000 retail. I'm not going to say how much we paid. But 5 years' time, it's not going to be £50,000. 5 years' time, you'd be able to probably get something like that. I would guess maybe 1,000.
And AMD provide APUs that are already that shape as well, and they have been doing for years. It's just NVIDIA haven't got a CPU vendor that they're particularly friendly with currently.
I think also building something like this, sorry, quick one, we can also have to be sort of clever in how we go about doing that. I mean, we got cheaper electricity in Sweden, so we moved to Sweden, and it meant we could have double the size of the machine but if we stayed in the UK. Now, I'm not saying that's the answer for everyone, but sometimes you make a choice so you can make sure something happens.
Yes, we still have one more.
Should we move to Fernando?
Yes,
He's been
let
waiting
somebody
for
in
a
the
long
room.
time. And then-
Yeah, Fernando's down there. Yeah, I will ask these questions of the panel. I'm telling people online, I'll ask you the questions and then I'll type them back in afterwards because there are still more.
Thank you. Hi, Fernando from Durham University. I have two questions. The first one is about open source hardware. So I'm sure you're aware of the European Processor Initiative, and I was wondering if there is something similar for GPUs or something likely to happen in that respect. And the second question is about procurement and environmental considerations. Do you think that there is going to be in the future a built-in consideration as to where the minerals mined to build the computers come from? Thank you.
So open source, and again, this is why I'm so sad that the world we're moving towards. The world we're moving towards is one where government and public are so afraid of the potential of AI and what it could do that actually open source is seen as a security threat, and there's a push to actually make the open source models and the data, releasing the parameters of the data publicly, an offence, a criminal offence. In the same way with open source hardware, because of the desire not to let certain countries advance technologically, even though they should be allowed to advance technologically, well, I don't see why we're stopping them, the funding, as far as I understand, on open hardware, and particularly if there would ever be an open GPU, that would just be blocked, because that would be viewed that you're giving a third country a technological advantage. And so there's been this kind of retraction of that you're basically not giving export control laws, you're not creating a design and sending it across. And I think this is what was basically stopping the open power and things like that. The reality is that the world we live in now is so different that the kind of open for everyone world, which I really like, that is now actively being attacked from people who have concerns, but also then being exploited by business interests who then raise those as concerns. You only got to look at what I said earlier about people looking at supply chain attacks and saying you shouldn't have open repositories, you need to have paid repositories, and they've all been scanned and everything else. And as someone who's a very passionate open source advocate, I think it's really sad that the making the sharing of weights of a machine learning model a criminal offence potentially in the US would be awful.
Okay, very quickly, anything else? I'm aware we've reached our time. So anything else from the panel? 5 words each.
AI is here to stay. I think
That
that
was
might be
6
6.
words.
Oh, do me last.
Okay, good. Right. Well, I think we will probably finish there unless people are desperate to stay. But no, let's have a break before the next session.